Thanks, Ben. Thanks for having me up here. I should say, Hisashi, he worked with me at UCSB. He came up from San Jose. He works for LumiLEDs, which is a first-tier LED manufacturer that does manufacturing in the Bay Area, which is a great thing that we have here in the U.S. Also, here's my aunt. Not like.
Also, golden food.
Yeah. So, and even though I grew up in California, I live in Tennessee now, which is a little different culturally and everything, but I like it. So yeah, I have a background in material science and electrical engineering, and I got sucked into lighting. And that's a lot of people come into lighting from different places because it's a very broad topic. There's a lot to it, and it's got more complicated recently with new technology and our new understanding of physiological responses to light that we need to understand much better. And that's people, plants, and animals. So we need to get a handle on what we call the stimulus, which is the light source that interacts with the room and the space, and then the physiological response, which is our eyes, including our non-visual receptors. And if we're dealing in horticulture, it's the plants and the people in the grow area. If we're dealing with animals, it's the animals that we're either trying to grow or that we're trying to not affect with our lighting. So there's a lot of work to do across the board, from the LED itself can still become more efficient to our understanding of what lighting means and how do we deliver the best light for the function that we're looking for. So that's why there's these three revolutions. The revolution in the middle, design, is pretty important because almost all of our lights look very much like the lights we had 10 years ago or 20 years ago, or in some cases 70 years ago, or some cases over 100 years ago, where we have lights that look like candles still. We haven't caught up the design to work with the technology. If we were starting with LEDs, would we really be making light bulbs? Would we really be making 2x4s in this configuration that we have in a lot of places? Maybe not. And then part of the design revolution is what manufacturing technologies can we bring to bear to be effective in making and delivering these products. Because lighting is such a large industry and it's semi-custom, every building is different. It's the economies of scale are a little bit different, and we don't want to fall into old economies of scale that we don't have to. We have an opportunity to rethink the whole situation. So, as Ben said, this revolution was ignited by the invention of these three scientists. I'm biased, but I think Shuji Nakamura played the biggest part in this invention of inventing the blue LED. You have to have a blue LED to make white light. We had red LEDs, we had some green LEDs, but without the blue LED, you can't make white. And if it's not efficient, that's not super helpful either. So this breakthrough is pretty profound, and I think it's going to have kind of century-long implications, just like the invention of the incandescent. I think it's on the same level. I was at a photonics conference earlier this week, and they had this poster of pioneers in optics and photonics. And it had, some of the old scientists like Fresnel, or people who came up with these early optical concepts and theory. And there's Thomas Edison in there. And so I took a picture of it because in my mind, Shuji Nakamura should be our most recent LED pioneer or optical pioneer. It's really a huge impact, and that's part of the story. And so when I started at UCSB in 2000, and I just met Shuji, I was applying for a job. He said, we're all going to be working in lighting soon. And I thought, that sounds terrible. Lighting sounds like the most boring thing to be working on. I was all into lasers and optics and semiconductors. And he was right. I'm working on lighting about 30 or 40 grad students from that program are all working on lighting in various parts of it, of the value chain. He was pretty far-sighted there, so it's not boring. It's very multifaceted and intertwined. So I like to show this picture. I don't know if you can see it. It's me, it's Shuji when I was finishing, and it's got my little guy there in a sweater vest. I try to get him to wear sweater vests now, but 13-year-olds don't go for that. So here's kind of the wheel. It doesn't stop. This just keeps going. We have technology developments. LEDs get better. We get optical control, intensity control, spectral control improvements, and then that lends themselves to new design improvements, new technology. I guess we could say we are here. We're at the technology advancement phase. I don't think the design improvements have caught up. We're still kind of relying on the old lighting infrastructure and the old lighting form factors. Application understanding, we're at the very beginning of understanding non-visual physiological responses in humans. We're at the very beginning of understanding how best to grow plants under electric lights. Even the old topics of color and color discrimination and glare and flicker, I think it all needs to be revisited. I said yesterday in a similar talk, if there's any lighting research that was done pre-LED, we need to do it again with LED technology. LEDs are a great research tool that we have intensity control. We can any color, any intensity, any optical distribution. All the old research was done with the old technology that had to use filters to get color control. They just couldn't do then what we can do now. A lot of that research has worked great. We have the lumen. We have good guiding practices that have brought us to where we are today. But I think we need to redo the old lighting research and also the physiological research and bring everything up to date. And that's a huge job. It's just part of my message is we don't have enough people. We don't have enough effort to steer this huge industry, this absolutely enormous industry with enormous energy implications, the enormous market, $100 billion a year market, 5 times that in energy or some multiplier, I forget exactly what it is. And then now we're talking about health, making people healthier and providing ways to make healthy people healthier, but also to make certain sick people healthier and do better. And then the productivity of plants, giving us a new opportunity to produce plants and animals in more effective ways. And that's just the big opportunities. There's going to be tens or dozens of smaller applications that come about because we have a good supply of controllable photons that we didn't have before. So yeah, that's all the impacts. We also need to spend some time really understanding the impacts and the targets and what we're working towards. So it's a little fuzzy, this figure, and I'm sorry, it's from a paper I wrote with some colleagues trying to bring this story together. I wrote a paper with a top-notch physiologist working on this subject, one of the discoverers of the non-visual receptor in the eye that we didn't even know about until 2000. And then a great horticulturalist who really understands plant physiology and plant growth. And then another technologist, U.S.A. from Sandia National Lab. So we wrote this paper, and if you look at the jump from kerosene lamps or fuel lamps to electric incandescent lamps went from just in terms of luminous efficacy from half a lumen per watt to 15 lumens per watt. That's a huge deal. It changed everything. It promoted electrification around the world. And now, over time, we got to the fluorescents, which are about 80 lumens per watt. And now, on the same scale, we actually have, I'll show a better figure, but we have LEDs that can do better than 220, 225 lumens per watt right now. You put them in, when you integrate them into a fixture, they don't do quite that well, but they can do very well. So we've gone from somewhere between 15 lumens per watt and 80 lumens per watt to 200 lumens per watt. if we even want to be talking about luminous efficacy, which we do sometimes, but not all the time. So that's a big jump. Shuji didn't do all of that, but he showed us how, right? And the LED companies have done great improving LEDs and bringing down the cost. So this is the same data, just a little better figure. And so they show the potential, and I'll show the difference between a color mixed and a phosphor converted LED. But for a phosphor converted LED, this is a DOE analysis. We think it can get to 250 lumens per watt. And we're pretty close right now. The reason why those data points are a little below 200 right there is that in this analysis, with this historical performance, we constrain the performance by current density and color qualities so that we have a consistent baseline. But if you underdrive, if you turn down the current, you can easily get to 200 plus lumens per watt right now and with reasonable color quality. So,
sorry, what is reasonable color quality?
CRI 80.
For CRI, like 95?
CRI 95, I think you get it to 200 lumens per watt. If you really worked at it, you could. But yeah. And then that begs the question, do we want to be using CRI or something more granular, TM30 or whatever, or more application specific? I think those fidelity metrics are really good when your job is looking at color differences. But when you're putting your light behind a lampshade, maybe that's not necessary. Or when you have a lot of daylight that washes out the color qualities of the lamps. That's where we get into more application granularity. That's part of the challenge, because buildings are all different and we have this technology that can accommodate a lot of differences. But yeah, CRI 95, it is a challenge because, and I'll talk about it too, you start bringing spectral efficiency into the discussion and trying to match power conversion efficiency with spectral efficiency and make the appropriate trade-offs. And that's where actually the bottom curve comes in, is where the discrete color direct emitter LEDs are at right now. So I'll go into this a little bit more in the next slide. There's two ways to make white light. The way that almost every product uses right now, LED ways to make white light. You use a blue LED and you put a luminescent material on top of it. And that's what that figure, the spectrum in the upper left shows. You have the blue spike, we call it, the blue LED. That some of the light comes through the luminescent material, typically a phosphor, and a lot of it gets absorbed by the phosphor and re-emitted as green or red photons. So it's the blue LED. It's really interesting. Right now, the blue LED materials are semiconductors grown in a reactor, what we call a reactor, metal organic chemical vapor deposition reactor, grown at 1200 plus degrees C, with almost atomic layer, control over the thickness while you're putting in alloys and various impurities to get the semiconductor just right. It is really a marvel how good these things are. And so with the blue LED right now, for every electron that goes into their light generating layer, it's like 90+% efficient. So 100 electrons go in, 90 photons come out, 90 plus. And then of those photons that are generated, 90% of those plus get out of the semiconductor material. That's called light extraction efficiency. And when you're delivering the electrons in, 95% of the electrons make it into the semiconductor. So you're dealing with better than 90% for all these sub-efficiencies. That ultimately gives you, depending on operating conditions, very high 80, 75% efficiency. And then you have the phosphor conversion process, which is also 90+%. And you have, some LED package effects, which are 90% also. So the one thing we can't control with the phosphor conversion process, though, is that when you're going from that blue wavelength to the phosphor wavelengths, there's an inherent energy loss because the blue photons are more energetic than the other photons. That's called the Stokes law. So when you add it all up together, your LEDs are, 50 or 60% efficient. There's a much more detailed analysis of this in some of our DOE documents. But the point is, with any light generating process or material, you kind of have the same or relatable efficiency breakdowns. There's not going to be something that's much more efficient than LEDs. They are so efficient. There's not a what's the next thing? What's the next thing after LEDs? I can't imagine that there is, because they're just too darn efficient. Now,
There's some laser.
lasers are much less efficient than LEDs. They project out that they're going to get better based on how red LEDs progress, but red lasers. Red lasers have some pretty different material science challenges. And then, with all lighting, basically we take bright sources and make them diffuse. We've done that for years. With a laser, you really exacerbate that problem and introduce some optical losses. But for spot lighting, for monument lighting, for maybe flag lighting, I think lasers could be the way to go, because they can put a lot more light on target. So you get better optical efficiency, and you're trading off source efficiency with optical efficiency. So that's definitely on the table. That's why people are working on it and looking at them for street light or headlamps, for car headlamps. So yeah, the blue LEDs plus the phosphor are great materials. It's like a match made in heaven, really. You've got the phosphor that's super efficient, super reliable, super stable, emits at just the right color to work with the blue LED that's super efficient to make, reasonable white light. And you can add some red phosphor in there and get higher color quality. You can change the thickness of your phosphor to get different CCTs. So there's a lot of flexibility in that system. In the upper right there are the other direct emitting LED wavelengths and their relative efficiency compared to blue LEDs. So they're not as efficient. That's power efficiency, watts out per watts in, relative. There are products now, more products that are combining direct emitting LEDs. The one benefit is that you don't have this inherent phosphor conversion loss. The drawback is these other colors aren't as efficient as they need to be to be as good as the phosphor converted approach right now. Now, with the DOE, what we say is we don't know that they can't be as efficient as blue LEDs. We don't know material science or physics reasons why they can't get there, but they're not there, and they're pretty difficult challenges to get there. So yeah, let's go to the next slide. And a lot of these figures are in the Department of Energy R&D. Basically, it's a roadmap. We call it the Lighting R&D Opportunities document. It just got released last week or 2 weeks ago, the most recent version. It's updated every year, and it has the R&D, the short list of R&D opportunities that the DOE is looking at each year. So, part of the technical change or capabilities of the LEDs is that we do have better optical control, and they're all inherently dimmable. Not every LED lighting product can be dimmed, but the LEDs are inherently dimmable, and they should always be, products should be selected to be dimmable. So in this, I got called out on this slide yesterday, but what it's trying to show is in this street settings in LA, when you're looking at these street lights from above where they're operating, you see light coming directly into the camera, right? It's kind of like when you fly over a city at night and you look down and you see not reflected light off the pavement, but light coming directly hitting you. That's just wasted light. That's due to poor optical control. The old technologies had large source sizes and limited options for optical control. Now, The comment I got yesterday was that you can make cutoffs and glare reducers with the old technology, but they're kind of clunky and expensive. The image on the right, what you see is little to no direct light being emitted in the upward direction. What you also can see if you look closely is that there's better uniformity on the road. And what's not apparent from this picture is that it's half the amount of light coming from the LEDs as from the HPS side. So you're doing the same job with half the total amount of light. That's a big change because you have optical control. And then HPS and other HID sources are hard to dim. They're hard to turn on and off instantaneously. Can't really put dimmers on them in the roadway. So what's happening now is that some cities, for example, Cambridge, Massachusetts, but also Tucson and San Jose, are putting time of night dimmers on their roadway lights. So that after everyone's done going to the bars, done having dinner, the lights turn down. So it's just another opportunity to engage the benefits of this new technology. One thing they also did in Cambridge, when they put in the lights at the beginning and measured the LED lights that were meant to be a one-for-one replacement with the HPS lights, they measured how much light they're getting, and they said, we're getting 30% more light than we need. So they just could turn them down and save 30% right off the top in their energy. So it's a big deal because if you think about it, this is the topic that's coming up a lot, is how much light are we putting into the environment? What's it doing to the environment? Well, if we can use half the total for half the time or less, we've just cut the light in the environment by 75% without even trying, without even working on that very hard. So that's a big deal. You know, those images, the satellite images of light at night, and in the old days, I think when we were all growing up, you'd see those and say, yes, we're so productive. We're emitting all this light directly to satellites. You know, and they're not in Africa, right? That was the mindset. And now we look at that and we just see, that's all 100% wasted light. There's no reason to be emitting any light in the upward direction. It does nothing for anybody. In fact, it's detrimental for a lot of reasons. It causes skyglow, it affects migratory birds, it affects animals. So that's another feature of this technology that we're just getting started with. And this
about efficiency with dimming.
What's that?
I had a question about efficiency with dimming.
Mm-hmm.
That you mentioned underdriving LEDs, and do they get more efficient?
Yes, they do.
Does the power supplies and the whole?
Nope.
Okay.
Nope. So LEDs do. So the lower the current density on the LEDs, we call it droop. When the harder you run an individual LED, the less efficient it is. But with power supplies, they're usually tuned up to operate at a certain, to have best performance at a certain operating condition. And then when you dim them, they go from 90+% efficient to 80 to, So that's actually an R&D challenge right now, is to make power supplies that maintain efficiency over their whole operating range and are multi-channel so they can handle different color LEDs and control the colors. So that's a good challenge that's not there yet. So those are the technology improvements that are on the table right now that we can engage. I want to talk about design improvements. Do you think this is the best form factor to jam LEDs into? It's not bad. It's backward compatible, right? That's okay. That threaded socket, you guys don't use those here in California anymore. The threaded socket's not great for thermal dissipation. Omnidirectional light can be really handy in a lot of situations, but maybe not in others. So it's really not a great form factor for the LED technology. Although I will say these filament lights are surprisingly good in terms of their performance and technology. And they look okay, but it's still, from a design perspective, from an aesthetic perspective, we're still chasing stuff from the past, right? Our chandeliers, look like candles. Our LED light bulbs look like incandescent light bulbs. There needs to be an aesthetic component to design, an industrial design component also that takes full advantage of the technology and isn't just looking backwards. I'd really like to get some artistic types to work on this, because most lighting products and chandeliers they're not very functional, and I don't think they look that good. And we have this whole new kind of palette of materials to work with. This is hard to see, but there is one trend I'm seeing, which is these flat downlights. You don't need to go into the ceiling anymore. These are all flush mount things. I've got one that's 2 feet wide in my kitchen. It's great. It's a lot simpler to install. That's, I think, a subtle change. We had flush mount lights before, but now we have much thinner, good performance flush mount lights based on the LED technology. That's going to keep going. Design changes like that. I did want to digress a little bit though. Back to the 200 lumen per watt discussion. This is a bulb. I don't know if anyone can actually buy it, but it's a bulb that's on Philips' website that they made to buy.
I bought it.
Oh, you did?
Yeah, I bought it.
200,
I bought a dozen back in the United States.
200 lumens per watt? Did you measure them?
Yeah.
That's great, right? I mean, and this is from several years ago. So, the message here is, why are we settling, even with the old form factors, why are all the products that are on the shelves in the U.S. less than 100 lumens per watt and still have crappy color quality, and a lot of them are dying early? We're really settling right now. A lot of the can lights, the integrated cans and integrated fixtures aren't doing what's possible. And so it's the market kind of wagging, or the market expectations of people going backwards, looking backwards, what they expected from the incandescent bulb. 50 cents a bulb, lasts 1,000 hours. And now our LED products are reverting to that value proposition instead of saying, look, spend $20 a bulb. How much does that add to your new house construction cost? Especially if you don't have to change it. We need to change the discussion and the mindset a little bit. Here's another nice concept. So new design, using new materials. The Department of Energy had a sustainable manufacturing challenge for manufacturing concepts, design concepts. This one was the winner. I think he won like $10,000. I don't know if any of you know Brad Kerner. He's one of the early employees at Color Kinetics. He's the one who won this. This is a concept where the fixture is made out of bamboo. The circuit board is made out of a flax material. It's all supposed to be biodegradable and part of the circular economy and have kind of low energy input. We're not really changing the material set very much. With most commercial products are still aluminum, same optical materials. We haven't had the revolution in design that we need to have. Yeah, you can see this on the DOE website. Part of the change in design, I think, is going to come about from change in manufacturing processes. This is just an example of some of the advancements in 3D printing. This is glass, 3D printed glass. Came out of some research at MIT Media Lab. There is a presentation on this just last week, and all the presentations from the DOE R&D workshop that was last week will be posted, so they're publicly available. This guy was showing what could be done with glass printing for possibly optics and for aesthetics, but the bigger idea is, how do you print the whole luminaire, additively on demand? And actually, there's a lighting company here in California, Tempo down in LA, that's working on that, making a lot of the parts for their fixtures, 3D printed. Eaton, Cooper Lighting, there's Eaton Cooper, it's Cooper and then Eaton Cooper, now it's Cooper again. They're trying to make roadway lights, all 3D printed directly onto the heatsink. The LEDs printed right onto, and the electronics right onto the heatsink. That's a DOE project. So, part of the new technology, part of the new story is, changing manufacturing processes and really looking for opportunities to re-engage U.S. manufacturing in, some parts of the value chain and expand U.S. manufacturing. Did you get your picture? So the other revolution is in application understanding. So a lot of people here, I think, work in an efficiency program. This is an energy efficiency center. There's a funny thing about working in efficiency is that you're trying to do the same job, but with less inputs, right? So the numerator stays the same, the denominator goes down. With this lighting technology and with what we're learning, that numerator is getting really messed up. If we're using more energy to grow more stuff, then it's productivity, right? And that's a good thing. We still want to do it as efficiently as possible, but we're struggling, I think, to characterize and clarify the benefit that we're getting for the downside, for either the energy or the environmental impact or whatever. And it's not just we want to do the same job as we've always done, just more efficiently. We want to do the new, better job that's really important and do that as efficiently as possible. So we've got a couple of moving parts. We've got the numerator is not well understood right now, and the denominator is changing and getting better, or going down, basically. But we don't understand everything in the denominator either, because we're struggling with these questions about light at night and the environmental impacts of lighting, and what's the trade-off between the function of the light that we're putting out there, the roadway safety or the visual function, versus the side effects, the downside. So it's a little bit different than a pure energy efficiency light, what we're talking about. And also, lumens are they're one of those 100-year-old metrics, lighting science things that needs to be reevaluated. That's going to be tough, but maybe we can add more benefits than just the lumen. We have to think about more benefits than just the lumen with the new technology. So one of them is health impacts. So like I said, around 2000, multiple scientists figured out that we have an additional optical sensor receptor in our eye that we didn't know about before, a new part of the body that we didn't even know existed. It's called the intrinsically photosensitive retinal ganglion cell, IPRGC. And it's a photodetector that we don't use to see. It basically detects night and day. And the peak responsivity of this photodetector is in the blue wavelength. And when there's bright blue light, like outside daylight light conditions, the effect is that melatonin is suppressed. It's alerting. It's like a cup of coffee, but with no side effect, right? Unless you get bright blue light at night, and then you're suppressing melatonin and you're affecting your sleep, which is a pretty bad side effect. Or you're in a dim room like this, and you don't have bright enough blue light, and we might be dripping melatonin when we shouldn't be. So our bodies are getting a little thrown off. In modern society, we basically go from one indoor lit situation that's not bright enough at home to another indoor lit situation that's not bright enough at work, and then back. So this signal, this night and day signal, or night and pre-sleep signal that we naturally should be getting, which is like this, has this much on off, we kind of get this in our lives. And they're starting to understand that there's some pretty significant health implications, especially for people who are already compromised in various ways.
How fast that receptor respond?
What's that?
How fast that receptor respond?
It's pretty fast. It's like minutes. Yeah. So yeah, it's something that now lighting people have to think about. This is probably one of the most important things to think about. And we have a technology that can help us out with that. So there's those LED colors again, the response spectrum for this IPRGC in our eye is kind of peaked up right around 480 nanometers. There's some controversy where it exactly is. This is a difficult thing to measure. And then there's some examples of light spectrum that either fully engage that receptor, the high melanoptic stimulation, or don't engage that receptor. So this would be a very cool white light or a very warm light. So yeah, it's just another thing that we have to think about with lighting going forward. This is my co-author on this paper. I like that picture because he looks like a scientist. He was my doctor. I really trust him. So in the studies that they've done so far, they have to control the studies. So we call them lab studies because they're controlling the conscious and reflexive behavior. They're controlling the ocular media transmission by selecting subjects that are in the same age group. They're controlling pupil dilation. They get enough subjects to control photoreceptor sensitivity and distribution, but not that many. And they're controlling the light and the photo history of their subjects. So these are highly controlled studies that have shown us how this physiology works. Now the challenge is, what does that mean in practice? How do we translate that research to practical situations? That's super difficult because none of these things are controlled anymore. Every person has a different light history and light diet, and we have individual variations in responsiveness to light. So how do you turn that into guidance for building designers or architects or lighting manufacturers? We're just not there yet. The other complication is that with this melatonin that we're trying to suppress, that alerts us, that's the acute response. There's also longer term responses that shift our circadian rhythms. And we know that that's a problem when we're trying to have people who are alert, but maybe not shift or engineer their circadian rhythm. We know it's a problem for night shift workers who get sick and die a lot earlier than day shift people. And a lot of our understanding of a lot of the understanding that people are trying to use about how to engage these effects comes from night shift studies, epidemiological studies of nurses, error rate studies of doctors. The problem is that's not what we're trying to learn. That's different than what we want for day people, where the melatonin suppression, the alerting, and the circadian impacts are all in alignment. So we got to be careful about translating research from night shift people to day workers. It's a completely different situation. I've been seeing that a lot, where a lot of the concern about light at night is based on night shift studies, where people are awake, working, and alert, and eating. For day workers, it's a completely different situation. We have to make sure that we're not mixing those up. What George, he actually has a nickname, Bud. What Bud says is, increase light exposure in the morning, decrease light exposure pre-sleep. It's as simple as that. And some of my work with the Department of Energy, I put together meetings. We meet with like 15 physiologists who are studying this in a room like this. We talk about this topic and what the R&D challenges are. And there's a group at Harvard, and they just say, where people are working and never sleeping, we should just have bright blue light, because we always want them to be as alert as possible to do their job as well as possible. That's it. That's one part of the guidance. And then the other part is anywhere where people are pre-sleep, or it's a dual function space where they might be wanting to be alerted and pre-sleep. That's where you have tunable lighting, or lighting that's dim and has depleted blue content. So the point is that those guys think that we might be overcomplicating the situation a little bit. If people are working, we want them to be alert. If there's a night shift doctor working on me, they're the near-term impacts of his alertness outweigh the long-term effects of his circadian rhythm. And that's some sort of trade-off that we're going to have to manage, which is it has huge implications. Just going back to this though, for healthy people, these effects are subtle. 1% healthier, 3% healthier. That's what a scientist from Stanford said. That's hard to sell people on the technology when you're talking, hey, you're going to feel 1% better tomorrow if you spend $100. People might or might not do that. It's a little bit like the energy story. Buy this expensive bulb and save, have a 5-year payback. It's hard to convince people, but society-wide, those are big benefits. If we can really convince people to do that, or if we can find a way to incentivize them. That said, dementia patients are a lot of times free cycling. They don't know what time of day it is. And then they're in a care facility that doesn't have a night-day offset in their lighting. So they're not getting the signal, so they don't sleep well. Care homes, old folks homes, a lot of times they never go outside. The lights are on 24/7. Traumatic brain injury, they're trying out better lighting, traumatic brain injury situations. Autistic people can benefit from these better signals. So there's like at-risk populations that can really benefit, and then there's the healthy population that gets a big benefit as well.
ICUs are a horrible problem.
Yeah.
Lights are on all the time where people get
Yeah.
minutes.
That's a really difficult problem because you have nurses that are on night shifts and have health implications. They need to do their job. They need to see things. You have patients who need to sleep, and it all gets mixed up, right? People running in and out, lights going on and off. It's a terrible problem, and a huge opportunity. I think in a few years we're going to look back at how we did lighting, which would be now, and just say that's crazy. that was really bad lighting. So another, function of lighting. So now we got to, like I said, be more granular about the function of lighting. It's not just providing lumens, it's providing some sort of service or value. So with roadway lights, we put lights outdoors for safety reasons. We don't really understand what makes a light safer or less safe. This is one study that showed that a relatively cool or neutral white LED light increased or had a longer detection distance at night to see something on the road, which means you have more time as a driver to respond. So this study would imply that the 4,000 Kelvin lights are safer than the 3,500 Kelvin lights, and the 250 and 400 watt lights are HPS and safer than those. Now this is just one study. I think, I got some pushback on it from the group yesterday. We need to understand what the best safest roadway light is. And it's not just going to be one size fits all because, you're turning off the road, you're going straight on the road, you have a mountain road. Roads are pretty different and you got to get the lighting right. But what I see happening is people designing roadway lights to not do something else, to not affect people's health or to not affect the environment. That's backwards. We got to figure out how to best do the job and then minimize the side effects, if that makes sense, right? So we can't choose a roadway light just based on the side effects. We got to make sure we really understand the purpose of the light, how best to achieve that purpose. Because now we have infinite options. We can make any color we want, any brightness we want, any optical distribution we want. LED companies, Hitachi's LED company, they come to these meetings that I have sometimes and they say to the physiologist or the horticulturist, they say, just tell us what light you want and we'll make it. Anything. We'll make anything that you want if you tell us that that's the best solution. What do we know right now? Only what we've done in the past. All we're doing is replicating the lighting performance that we've had. There's a lot of research that needs to
You're
happen.
saying these are street lights or
Street lights. That's another challenge though, is there's so much lighting research that needs to happen. And it's been so static for so long, the technology, that I think we're understaffed to do all the research that needs to happen. This is a vertical farm, horticultural lighting. Yeah.
Sorry, forget my gap in knowledge, but what is a Kelvin?
Okay, Kelvin is how you describe the color temperature, the hue of a white light.
So that's equivalent to like black body temperature.
Exactly. So lights, incandescence 2700 Kelvin. Fluorescent could be 4000 or 5000 K typically.
So that tells us the color.
Yeah. So the cooler, this would be categorized as a neutral white, 4000 Kelvin. 3000 is warm, and 5000 is daylight if you're buying them at Lowe's or whatever. So there's a big opportunity to become more productive growing stuff with electric lighting. This is Aero Farms in New Jersey, the largest vertical farm in the world. This one, I think, is 2 megawatts of lighting in it. And these horticultural lights are trying to get them down to $1 a watt. They're more like $2 a watt right now. So $2 million worth of lighting happening, and all the time basically. They operate 24/7. That's pretty impressive. And we're just starting on figuring this out. We're at the very beginning. Here's just a guide. When you're talking about plants, we definitely don't want to be using lumens. We're talking about the characterization they use is how many photons within the photosynthetic active window are being emitted per second. And they count them up in micromoles of photons per second. So instead of lumens, you have micromoles of photons per second. Instead of lumens per watt, you have micromoles per second per watt or micromoles per joule. Instead of illuminance and foot candles or lux, you have micromoles per second per meter squared. So it all trickles down pretty much the exact same way as the lumen, but a different response curve than the eye response curve. This is kind of an agglomeration of the plant response curves.
You define these numbers for each plant.
No, this is for all plants. They do that for a reason. They don't know enough, number one. And I'll show you in the next slide, if you take all the plant responses and kind of average them, it looks like a box where you would count every photon the same. Now, it's not as cut and dry as that, but I'll get there in a minute. So I showed some LED performance curves earlier in terms of lumens per watt. We just translated those into photosynthetic photon efficacy. It's the same raw data. Right now, there's products, new horticultural lighting products that are putting out 3 micromoles per joule. So that means the LEDs are like 3.2. You can only really get there with the blue-red combo and not a white combo. So that's what the 2 different lines are. The conventional product used in greenhouses and marijuana grow operations are high pressure sodium, and they're 1.9 micromoles per joule. So we're getting 50% more efficient with LEDs. And we're already seeing that. So, like I said, we're not counting power, we're not counting photons. So if you translate those spectrum from spectral power density or distribution in terms of optical power and translate them to just photon counting, which is what's used for horticulture, you see a bump up in the red LEDs because they're measured or they're characterized differently, and they're just as efficacious as the blue LEDs. Now, the interesting thing, it's a little bit jumbled, but the photosynthesis response peaks line up almost exactly with the red and the most efficient red and blue LEDs. And people were trying to take advantage of that. And that's why you see a lot of magenta horticultural lights. I think they overinterpreted the information. The photosynthetic spectral response curve is based on what they call the McCree curve. It's named after the scientist who figured it out. It was performed in low light conditions. These plants are not being grown in low light conditions. They're being grown in very high light conditions. And there's a lot of receptors in the green part of the spectrum. And you can't simplify the function of the lights in that way to neglect the person who's in the grow room and needs to look for nutritional deficiencies and parasites, bugs, and all this mold on the plants. If you take out part of the spectrum, they might miss something. They might ruin a crop. So the trend now is even though they're slightly less efficacious, to use white LEDs with red supplements. So here's an analysis I'm working on with my colleague from U.S.A, Bruce Bugby. One interesting thing about my colleagues, Bud Brainerd and Bruce Bugby, is they've both been funded by NASA for decades to understand, on one case, light people, astronauts, but still does, he designed the lights that are in the space station. And what Bruce Bugby works on is figuring out how to grow plants on Mars. And so that's what now the lighting industry, the information the lighting industry is using to do better here on Earth is that foundational research. But, so you've got the power efficiency, watts, optical watts per electrical watts. You got the photosynthetic photon efficacy, micromoles per joule, and the relative price for different kinds of LEDs. What you see here is using maybe cool white plus red LED combinations are a good compromise between cost and efficiency, and lets you see what you're doing. You can set boundaries, based on understanding of plant physiological processes and the understanding of how plants fix carbon dioxide and water, the carbohydrates and oxygen. You can define kind of a practical theoretical limit of how many, of photons to biomass. And then from there, we can figure out electrons to photons. So we can know the cost of electricity per biomass in these controlled horticulture situations. And there's a great discussion in this paper all about this. It sets like some kind of practical physical limits on how many photons will get you how much biomass. So then from there you can work back. If you have a pound of lettuce, how much did the photons cost to make that pound of lettuce? And what you'll find is that for some crops, it's too expensive. It'll never work to grow them indoors. It'll never be economical because LEDs can only get so much better. And electricity, it kind of costs what it costs. It just won't be economical. Now, for some crops, high value crops, the math totally works. Microgreens, basil, marijuana right now. Probably a few more that are more niche. For wheat, for rice, it's not going to work as a sole source, using electric lighting as a sole source fuel for the plant growth. Now, there's a hybrid solution, greenhouses with electric lights where you get free light plus supplemented light, which changes the equation a little bit. But a lot of people are selling the idea of vertical farms. I think it takes a little bit more analysis. The other thing is the light level and the light wavelengths can affect the color. You're engaging different receptors in the plant, so you can make red leaf lettuce more red, is one example. So you're changing the nutritional content and the perceived value of plants based on the light recipe. And then we have talked about people, we've talked about plants, and we have animals. I'm just showing wild animals here, a couple of at-risk animals. You have the Newell's shearwater, which is a migratory bird in Hawaii, which gets disoriented by roadway lights out there, and when it lands, it gets disoriented, lands. They can't take off from a flat surface. These are cliff dwellers. They jump off and fly. So they're in big trouble when they land on flat ground. They're an endangered species. That's a problem. And turtles get disoriented by coastal lights. Instead of hatching and going to the water, they hatch and bar, they go towards the city, right? So that's a problem. I do some work with the National Park Service and go look at national parks and see what kind of solutions people have come up with. Here's an amber light in a bathroom. I don't think it's the best solution. It's just, it was kind of funny to me, so I took a picture. You know, like I said, the job of the light is not to not do something. It's got a primary function first, and then you have to look at the side effects. If the side effects so outweigh the function of the job in terms of your planning or consideration process, you shouldn't have lights there. You should just get rid of them. You know, they shouldn't have had lights facing the coast where the turtles are in this restroom. Could have put, or sorry, windows facing the coast. They could have put the windows on the other side, used a white light, and you know, done a better job. That's at Cape Hatteras National Seashore, at the bottom left there. These other red lights are something they tried out at Harper's Ferry in West Virginia, Storer College. I think it was a little bit overkill. I don't think they're doing their job. But there's now, at least there's options. We need a lot more research on animal responses to light, and that's pretty complicated research to do. You know, can't ask them how they feel. And then there's behavioral impacts as well. So they receive the light and then they do something. And you know, insects are a problem with roadway lights. That's a big problem. Birds, bats. This is something that's part of lighting now, is to figure out how to use lights more responsibly. So we have a new light source. We have all this new understanding, and it's just a lot to think about for any lighting application. There's like a gazillion things you have to think about now that we didn't have to think about before, and we're still figuring out what the right answer is for each different lighting application. There's a huge energy impact with this technology. The y-axis in this figure is quads or quadrillion BTUs of primary energy. That includes all fuel for cars, fossil fuels for industrial processes, all the energy we use in this country. Total amount is around 100 quads per year. We have the potential to save 5 quads through more efficient lighting. Now, different analyses show different stuff, but I think there was a researcher, economist at Berkeley, who showed that there's already measurable energy consumption reductions because of LED lighting. If you can measure it on that scale, that means it's something pretty serious. Now, by this analysis, we're already saving a quad a year, 1% of the whole energy budget for the U.S. Each quad is worth about $10 billion. So that's a pretty big impact, not to mention, of course, all the negative side effects of generating energy. Horticultural lighting energy is actually pretty big also. And there's a report that the DOE put out in 2017. We're putting out an update any day now that actually includes animal production, lighting energy used for animal production also. There's 3 different kinds of horticultural lighting applications that we analyze. On the upper left, we used a picture of basil when we wrote this report because DOE didn't want us saying the word marijuana. But that whole non-stacked vertical application is actually marijuana. We can say the word marijuana now. The middle one is supplemented greenhouses where you're using natural light, also with electric light. And then the one on the right is vertical farming. So there's a potential if we changed all the HPS lights in the greenhouses and marijuana farms to LED lights, you can save 24 TBTUs per year, $240 million. That's not bad either. Here's some of the details from that analysis. Like I said, this is available online, and then there's a new version coming out. What's interesting to me is that vertical farming is only about 10 acres in the US right now. It's pretty small. It gets a lot of media hype, but it's a tough business. Supplemented greenhouse has the largest footprint, but their lighting energy use is actually not very dense. They're not on very much, and they're spaced out pretty wide. Now, for marijuana, which is the right column, there's a pretty large area. And the lights cover a 4 foot by 4 foot area. They're on about 18 hours a day, and they're 1,100 watts. So it's a huge energy consumer. If you ever go into one of those operations, you need sunglasses. It's a lot of light. We know that you can trade out a 650 watt LED for an 1,100 watt HPS, and it'll still work. Now, what people do though is say, oh, what if we had a 1,000 watt LED? We want to grow more, right? So it's not just about saving energy. We have to consider increased productivity. So everything we're talking about was enabled by a more efficient light source, a more compact light source, the invention of the blue LED and the phosphor, and developments in the other color LEDs. But we need new design thinking, so we're not looking backward, and we need new application thinking, so we're not looking backwards when we're using this technology. We want to, while it's new and fresh, we want to figure this stuff out, so we're doing it right for as long as possible, for the next 100 years. This is like a once in a century opportunity. So that's it. Thank you.
Thank you, Michael.
Morgan.
So I'm supposed to give you a gift. Right. So you get to take something with you which fits on the airplane. You won't get arrested or some sort of thing. That was great. I learned a lot. You really liked it. And
Take questions too, if anyone.
Vertical farms of look and things, I'm sure they generate lots of heat as well.
Yeah, they need a lot of.
Do they recycle that heat to be efficient, or just they?
No, I don't think so. I mean, the plants like it a little hot,
Yeah, but probably
but
exceedingly
they
hot.
do use a lot of cooling. And all indoor marijuana uses cooling also. You have to use cooling and dehumidification in both those situations. So that's a lot of additional energy not counted in this analysis.
I was wondering if this is a trick for you, because it's almost like you deliberately wanted to make this increasingly difficult to discern for us who have some color blindness. Especially this one.
Visual
comfort, no glare.
It looks a little different on my screen, but
Yes.
no, it's not a trick.
Okay,
I
okay.
wish I thought of that.
Yeah, I think I recommend that. Are there any other questions? I did confirm that, the Dubai labs were using. Yeah, and I'm trying to get you the report.
Oh, great. All right, I'd love to see that.
Based on countries, which countries are very active in these kind of research? Like U.S., probably one.
I don't know the status of the physiological research in Asia. I know the U.S. is very active, in Europe and Australia on the light physiology stuff. That's where I'm hearing most of the stuff, but that could be an English language bias. No, I don't know. But that's who I rely on to get information. I mean, some of the previous research on SAD type of stuff out of Scandinavia, it's really a specialized field, and people are coming and doing it. And Harvard has really had a historical program in this for about 40 years. They've done a lot of work on firefighters, tugboat captains, how to sleep science, basically, how to make sure they can perform in the middle of the night. And they've transitioned that to the lighting element as well. But yeah, it's mostly kind of individual stuff here and there.
These countries, I mean, the US DOE is spending big money on that?
No. So, like any research program, you can't do everything you want to do. Either you don't have enough money, or you get told you can't do things, like work on people.
Or marijuana.
Or marijuana, yeah. So DOE has had 2 projects, one on night shift work from U.C. San Diego, and one on the impacts of roadway lights on melatonin and drivers. That's at Virginia Tech. And that Virginia Tech project is just wrapping up. And the UC San Diego project, actually, the PI moved from San Diego to the Uniform Services University, and it got really complicated how to transfer the money, so that one's kind of on ice right now. Those projects were selected maybe 3 years ago. In the intervening couple of years, DOE did not select any R&D in this topic, unfortunately, because time is now, but they have a renewed focus on building. The lighting program at DOE is within the Building Technologies Office, and they have a renewed focus on building occupant health. So we're right there. We've been doing it before they told us we could.
As a failed applicant for some of that funding, I can tell you that it's disappointing, but it's good to hear that maybe they're switching.
Yeah, it's always, I'll tell you, as much as I know, it's very,
Keep it on, remember, you might be listening.
it's very competitive. It's always very competitive. And yeah, things come and go. They come in and out of favor. So.
I want to make sure that there are any more questions.
I don't know if we can see questions.
I have no idea, to tell you the truth.
It's okay.
So we're going to live dangerously and hope that that's the end of it. Thank you very much.
Sure, thank you.
And are you staying around here for a few more minutes? Or what's
Yeah, I'll be around.
Okay.